When it comes to maintenance planning on transportation infrastructure, such as a network of bridges, it is often the case that decision makers face challenges relating to adapting to certain realities. And those realities could, for example, prevent them from following a certain optimal policy. So, for that reason, a decision maker might need to know what kind of costs that they are dealing with in case if they want to delay the repairs or maintenance on a certain bridge against another bridge or versus another bridge. So this research work addresses such a challenge by providing a framework or a model that would enable quantifying such a costs that are related to delaying maintenance on transportation infrastructure. My name is Zachary, and this presentation is have the content from a paper that has been recently published under the same title of this talk. So we can start with the context to provide some foundations about decision making and structural health monitoring. So in this graph that you're seeing here, where we have nodes and links, you can imagine this as a sample from a network. And in general, in order to have a decision-making framework, we need to perform structural health monitoring on the transportation infrastructure. And that in general is done using visual inspection data that is collected at the element level, where an inspector would go on site and would evaluate the health of the structural components of each bridge. Now, this data would provide foundations for a deterioration model. This deterioration model is done at the element level. However, that element level granularity can be aggregated to get to a bridge level, and that would give us an overall health rating for a given bridge in a given network. Now, this deterioration model that's based on visual inspections can provide foundations for decision making. However, we still need to know what kind of repairs that could be performed for decision making, and more importantly, the effect of these repairs. So for example, if I'm doing repairs on a beam, how much improvement I can achieve with that repair on average. So that's something that has been done in a previous work, which is quantifying the effect of interventions. And also, in addition to the effect of interventions, we need to know the costs that are associated with each intervention. So these components provide foundations for planning maintenance on transportation, or designing frameworks or models for planning maintenance on transportation infrastructure. Now, why do we need to plan maintenance on transportation infrastructure? Why don't we just maintain all the time? Well, the main reason is really the costs. So in general, if we maintain all the time that structural component on any bridge need maintenance, then what we would have an elevated cost profile over time. So it's not only about the current moment, but it's also like over time, up to time t in the future. So this is if we maintain all the time. Now, what happens if we maintain only when it's really necessary? What would happen is that we're gonna reduce the costs, the total cost at the present will be reduced at time t. However, in the future, there will be consequences. There will be cost consequences that are much higher in general if we were kind of following some maintenance policy. So that's why you see in the present we would have a low costs, but later on in the future there will be some incurred penalties and costs associated with delaying maintenance for too long. Now, the reason then when we have a certain optimal maintenance policy, what we seek is really a kind of a cost profile that between the two extreme optimally, and that aim to reduce the overall cost over time for an infinite planning horizon. So this is really the reason why there are benefits in following or creating an optimal maintenance policy. Now, we know why we need a maintenance policy, but there are really challenges, big challenges when it comes to network scale maintenance planning. And these challenges are mainly related to the scale. This is the the focal point whenever it comes to maintenance planning challenges, is that what we are dealing with is decision making at the element level. So you can imagine you have hundreds of thousands of structural components that are all deteriorating simultaneously over time. So you need to make decisions at each year. You need to make decisions for all these elements, and each one of them would have different kind of action, and each one of them would have different kind of effect of improvement. So the scale of the problem is really significant. The other part is also uncertainty. So in general, when we are talking about uncertainty, is the fact that it's not necessarily the case that every time you do an intervention you would get the same effect. And if you're taking that over an extended period of time, then those kind of variations in the effect of improvement for different kinds of actions would have a large uncertainty in the future as we were moving forward in the future. So this is one of the challenges that decision making or network scale planning frameworks need to deal with, and this is also one of the significant challenges. Now, the last part with the challenges is that there's also the hidden contextual knowledge. So, for example, we have our network planning framework that produced or gave us a certain policy, and the goal of the role of the decision maker is to kind of validate this policy and pivot in case if there are some obstacles or events that prevent the application of that optimal policy. So this hidden contextual knowledge is in general not known for the decision making framework because of new events that arise, and that would add some complexity to network scale planning. So what we are doing in this research work is that we are offering an alternative perspective. And this alternative perspective is that we have this network. So instead of seeking to have a full decision-making framework that would identify an optimal unique policy for this network, why not we examine the incurrent penalties? So instead of looking at the optimality on network scale, why not we look at the costs that would be incurred if we don't follow the optimal policy locally for each bridge? So what this provides, it would provide the decision maker with a tool that would tell them about over time if we defer or delay our interventions, what is the incurred costs. And this research work is tackling this particular challenge. So the research objectives for this for within this talk were to quantify the cost of delaying maintenance for a structural element, because as I mentioned, the deterioration modeling is done at the element level, as well as quantify the cost of delaying maintenance on an entire bridge level. So this is for the first part. And what we've done also a validation analysis of the proposed framework performance on real data from the network of bridges in the Quebec province. So these are the two main objectives, but before we tackle them, I just want to provide some fundamentals about decision making. So whenever we want to talk about decision making, we talk about deep reinforcement learning, which is a decision-making framework that best exemplified by a video game. We can provide an example for that. So, for example, when you have this Super Mario video game, in reinforcement learning, we have some terminology called the agent. The agent is Super Mario that we have here. The environment in reinforcement learning is the Mario world, so the Mario level that we have here currently. The actions are the movement, so or like being able to jump or all the other kind of actions that Mario could perform. And the rewards, basically Mario would, or the agent would get a reward if they were able to finish this level or complete this level. So the end goal for reinforcement learning is to learn a policy that would maximize the total expected discounted reward. So this is whenever we have this this Mario game, it means that we Mario would earn a reward whenever the agent finishes the agent controlling Mario finishes the level. Now this is for something called single agent reinforcement learning. If we want to extend this, we can give an example for a multiplayer game. So here where we have a multi-agent, and this is for a soccer game, for example, you have the magenta agent, they are playing the soccer game. It's really the same principle, except that now instead of having one agent to control, you have two agents. Each have their own set of actions, movement or shooting the ball or whatever. So that's why you see that here we have represented by two controllers, and the rewards basically would stay the same. It's the end goal is to win the game and learn a policy that maximizes the total expected discounted rewards. So for this particular game, it becomes more complicated because now the agents need not only to win on their own, but also to learn to cooperate. So the policy becomes a little bit more complicated. Now I'm gonna justify why I'm bringing up multi-agent reinforcement learning, but first I want to draw the analogies to transportation infrastructure. So in transportation infrastructure, it's the same thing. We have an environment where we have a structural element that is deteriorating over time. And this structural element, because we want to, if we perform repairs, for example, so the deterioration here is represented by the red dashed line, the uncertainty or the confidence interval around it. And we have here the blue point here is the inspection point. And here, for example, we have an intervention that happened at the year 2016 that improved the condition of this structural element up to this point. So it's really in the high 90s. And then here we have another inspection at year 2018. So this is kind of resemble the environment where we have the agent as the decision maker made the decision to intervene in the year 2016. The environment is infra planner that we have here. The actions would be to do nothing. So for example, in 2014, we did nothing. 2017, we did nothing, and so on. Or to repair. So here, for example, in 2016, we do repair or replace. And the rewards, basically, this time would be the rewards is the expected costs. So the end goal would be to minimize those expected costs in general. This is how the problem can be formulated. Now, this is for one element, so we can think of it as one agent that needs to learn how to minimize the costs using these actions. Now, as I mentioned earlier, we have thousands of elements. So whenever we have multiple elements, we would have, it's as if we are having multiple agents that are the decision makers, making decisions or learning how to make decisions on each structural element. And also each element here would have its own set of actions. So the idea here is that the decision makers as well need to learn how to cooperate in order to minimize the total expected discounted costs over time. Now, for in general, this is if we're gonna have one agent per structural element. As I mentioned earlier, we have hundreds of thousands of elements. That is really infeasible. At least currently, it's infeasible to have one agent per structural element. But instead, what we can do in order to simplify the problem, we can have one agent per type of element. For example, if we have all the concrete beams, if we assume that all the concrete beams are deteriorating in the same way and go through the same type of defects, then we can have one agent that learn the policy for how the concrete beam structural elements are deteriorating over time in bridges. So that's one simplification that would improve the feasibility of applying such a framework. But still, even with such a simplification, if you have a network of 10,000 bridges, or let's say even 5,000 bridges, scaling such an environment where you would have 5,000 bridges, and let's say you have on average 10 agents per bridge, that is a large number of agents that needs to learn how to cooperate and learn a policy that would aim to minimize the total expected costs. So we're still having the challenges of scaling the problem. And that's why examining an alternative perspective where we aim to have local optimality instead of global network optimality would be more practical and more feasible to be implemented in practice. So for that reason, we can take a look right now on how we can learn an element level policy, and then we can see how we can use that in order to get to a bridge level policy and how our framework is formulated. So basically we can start by an example at the element level for the slab. So here the environment would be to learn the optimal maintenance policy on how to repair or perform maintenance actions over time for a slab element. So, for example, the environment would be the deterioration over time for slab elements. So what we have here on the left, we have the condition, the deterioration condition, and this is just an example. This is not the actual environment, but just an example to show how the deterioration is happening over time. So on the x-axis we have the time on a yearly scale, and on the y-axis we have the condition for this graph. And the blue points here are the visual inspections performed by the inspectors identified by these IDs. And the blue whiskers here, they are the uncertainty associated with each inspector, which is quantified using a framework that was introduced in previous research work. So the deterioration condition is the red dashed line with the confidence interval around these. So here we see the prediction over time for the condition, and we also have access to the deterioration speed, at what rate the deterioration is happening in that element. So these two components, you can think of the expected value of the condition and the expected value of the speed over time, can be used as an indicator about the environment or the current state of that structural component. So this is what we mean by environment. Now, on the other hand, the kind of actions that we can take in this environment would be do nothing, which is let the element deteriorate, routine maintenance and preventive maintenance, and repair. These are different kind of repairs that have different kind of improvement levels. And we have also the replace, which is it's as if resetting the environment at condition 100. You start with the new structural element. So this is really the general idea. So using an environment based on these and having run multiple simulations in different states and different starting points, and letting the RL agent learn the policy, we get to this policy. So this is the number of steps it takes an RL agent to learn how to optimally interact, or basically act on the structural element, so that it minimizes the total costs. So you see the total costs here are getting to a state that is stable at the end of the training. And this is what the policy would look like. So for each action, we have the image here where the x-axis is the condition this time, and the y-axis is the speed. And each pixel in this image, for the slabs, for example, we have the do nothing, it's in this corner, and then we have preventive maintenance, routine maintenance, and repairs, and replacement presented by the yellow region. Now, what you see here in the red frame that we have here is kind of the penalty zone, where by definition a decision maker would replace because the state of the element is just too poor and it's unsafe to keep the element. So that's why any decision maker that would observe the element being in this kind of region would say we need to replace that. So this is the penalty zone as we refer it. And the reason why it exists is that it gives incentive for the RL agent to take actions. So if we want to move forward and look deeper into how this maintenance policy is learned, well, the learning process happens using something called the Q function. So we have an optimal Q function, which give us kind of the total expected discounted rewards for each combination of state and action. So this is what the role of the Q function. And in general, this Q function can be learned using a neural network, or there are other types of methods that would provide us with the Q function. So basically the policy, or the optimal policy, is that for any given state, I would give you the optimal action. And that optimal action, the AT, is in reality the maximum over all actions. So if we have the state and we have different actions here, a vector of actions, so that this action here is the maximum, is the action that maximizes this Q star function. Now, if we wanna, but this is if you want the optimal action. Now imagine the decision maker said, I can't make the optimal action because of certain constraint or certain event, we cannot take it. So then if we have this action A bar, which is not optimal, then we would have an incurred cost because of this taking the suboptimal action. And this incurred cost delta can be defined as the difference between the Q function of taking the suboptimal action minus the Q function while taking the optimal action. That's why it's the Q star here. So this is the delta, which is the difference, which is the incurred cost, we can call it, for taking the suboptimal action. Now this is for one time step t. If you want to take it for multiple time steps up to t capital, then we would have the discounted incurred costs over time, where gamma is the discount factor. Now the further details about this derivation are available in the paper, again carrying the same title of this talk. Now we can improve the interpretability of this incurred cost by using a ratio, where this ratio is really the summation of the, you can think of the optimal policy plus the incurred costs over the cost of the optimal policy. So in general, if we are following the optimal policy, delta t here will go to 0, and we would have RT equals 1. But if we are not following the optimal policy, then we would have a value greater than 1, because delta t would be always positive. That is assuming that our learning for the Q function is the correct learning. So this is what we are saying here, is that it's going to be either greater or equal to 1, the RT, which is the cost ratio. Now this is for one element. If you want it for an entire bridge, what we can do, one approach that can be done, is to have these incurred costs weighted. And this these weights, the omega p, they gonna be within category size ratio. So within the beams category, what size, if all the beams have an equal size, then the contribution to the incurred costs will be equal. So this is really the idea here behind this kind of function. So this is the cost ratio for a bridge. Now if we want to put together all the framework, just to show or reiterate on like what are the ingredients. So we have an element within a bridge. This element E would give us the inspection data Y, and it would give us also a weight, and this weight is basically the size of the element. Again, if all the elements are equal size, then we would have 1 over the number of elements as this omega p weight. So the inspection data goes into the SSMKR, which is our deterioration model based on state space models. This again discussed in previous research work. And the SSMKR would basically give us a deterioration state. as we saw earlier, we have the condition that we have here, and we have the speed, the deterioration speed, and we have the covariance and between these two states. So what we can do, we can take a sample from this current state, a sample of condition and speed, and this state, we can pass it into the policy to get the optimal action, and that would give us the Q star. And we can also pass the action of doing nothing. So this is the suboptimal action. And this is our state. And from there, we can calculate the incurred costs for a single element. And if we incorporate all this information, including the weights of the elements, we can have one realization at one sample from the one realization from the cost ratio distribution for a given bridge at a given time t. So this is really the principal idea. At a given time t, these are the samples, or how we calculate each realization. Now here we repeat this. We can take multiple samples in order to get a full distribution here for combinations of speed and condition. So this is really the general idea. Further details are available in the paper. So let's take a quick example on this. If we take in a bridge which has 15 beams, 2 front walls, 3 slabs, 2 guardrails, and 4 wing walls, 3 pavements, and we want to learn the maintenance policies for each one of these components. So for the beams, we have this policy. It's really similar to what we've seen earlier for the example with the concrete slabs. So this is for the beams, where on the x-axis we have the condition and the y-axis we have the speed. Same thing for the slabs, front walls, and all the other components that we have here. So these are the kind of optimal maintenance policies for each type of element. Now, if we want to take, now let's take from that bridge, these are the inspection data for the slab structural components. So on the x-axis we have the time, on the y-axis we have the condition. The visual inspection data represented by the blue points, and the uncertainty associated with each inspector eye that we have here. This is the condition with the confidence interval, this over time, and again the expected condition is the median is the red dashed line, and the same thing for the speed. Now if we use this information as a state and pass it into our function for the incurred costs, we get this figure, where this figure we see at the years, at the early years, in the year 20. So on the x-axis we have the time again on a yearly scale, and on the y-axis we have the cost ratio, and basically here we have the confidence interval for 50% and 95%. And the idea here is that if we let the structural element deteriorate over time up to the year 3031, as we performed here our deterioration state estimate, we would have an incurred cost of 1.5 the total discounted cost. So this is an additional cost that would result if we don't intervene before this year and just let the element deteriorate. So this is for a slab structural component. Now if we want the category, slab structural category for a bridge, we would have the same deterioration state estimate. Now here is the deterioration state is aggregated. So again, same timeline and condition on the left, speed on the right. And these are the aggregated observations, visual inspection data for the slabs category. And this is the deterioration condition estimate and the speed on the left condition, on the speed on the right, and it's the same time frame for the analysis, and we get this curve for the cost ratio again on the time. This is for the structural category of the slabs in that bridge, and it's used aggregation, given the aggregation is performed using Gaussian mixture reduction approach, and the weights of that Gaussian mixture reduction are determined by the weights, by the size of that component relative to all the slabs within the bridge. So we see the incurred costs here. If we let all the structural categories, all the slabs in the bridge to deteriorate, we would have it somewhere around 1.4, 1.45 if we let it deteriorate until the end. Same thing, but for a bridge, for a condition and speed, and these are the aggregated inspection data. We see that the deterioration expected condition represented by the black dashed line for the condition of the bridge, and same thing for the speed. And if we rely on such information, we see this cost ratio that is related to, if we don't intervene again, we would incur a total discounted cost in the future by this magnitude of the original total discounted costs. So this is what this one is implying, alongside the confidence interval, the 95 and 50 confidence interval. Now, there are further analysis and results that are present in the published paper, but this is really a brief summary of the results and what basically can help decision makers in making or taking better or more informed decisions. So in summary, what we've covered here, we've covered not necessarily a decision-making framework that would replace the decision makers, but it's really a decision support tool that would help decision makers in reducing, we can say, reducing decision mistakes or errors. So the idea here is that we can examine, using this decision support tool, we can examine the long-term locally incurred costs for each structural component and each bridge. And in case if there are other costs that are associated with maintenance delays, these costs can be integrated in the analysis. They can be added in case, but here is basically, for the first point, it's taking care of translating deterioration information into incurred costs information. And the other part is to emphasize that these results are really dependent on the cost function. So you have to make sure that we have to make sure that our estimation of the Q value function, which is estimated using deep RL, we have to make sure that the estimation is correct, and we have also to make sure that our definition for maintenance costs is accurate. Based on that, we can get correct or accurate, relatively accurate results about the incurred costs resulting from deviating from the maintenance policy. So these are the main points or main points of conclusion from this research work. And for further details, you can always have a look at the paper.